So the next speaker, it's Ernesto Lupercio, who will speak on a model in Quantum Toric Geometry.
Well, thank you very much. It's so nice to be here after all this time. And so I'm a little bit out of practice, like everyone. But in any case, I would like to thank the organizers and well, I'll start. So what I'm going to do today is to do a little survey of quantum toric geometry that we have been developing with Lvm Katzarkov, Lvm Meersseman, and Alberto Verjovsky at UNAM. So I'll give a little survey of quantum toric geometry, and then I'll explain a little bit the latest developments. I'll try to get to moduli and a little bit of mirror symmetry, but well, we'll see how far I get. So, most of what I'm going to say today is in this paper by Lvm, Laura, Alberto, and so you can find most of the details of what I'm going to say there. In any case, we know classical spherical geometry. In this crowd, I don't need to be too detailed. I will just say that a very important character in classical toric geometry is the torus, real and complex. This is the d-dimensional torus, and C star is C minus 0. So we have the real torus, and we have that typically we had that the action of the real torus is Hamiltonian, and we have the image of the moment map. And the image of the moment map is a, well, if this was scalar, this will be a polytope. Yeah, and this was compact. This will be a compact polytope, convex, rational del Sands polytope. That is to say, it's a combinatorial dual of a triangulation of the sphere, SD minus 1, and all the slopes of all the edges are rational. And this rationality condition is what characterizes the classical toric geometry, the rationality condition. So the situation looks a little bit like this. Here you have the moment map. Here you have the convex polytope. Here you have the fixed points corresponding to the vertices. And there you have the inverse image of a typical point is a real torus. And well, so what is quantum toric geometry? Now I can say what is quantum toric geometry after we have this picture on the screen. And is replace all the tori here, both the big complex torus acting and all the real tori here by quantum tori. So if all of them become quantum tori, then you get a quantum toric variety rather than a classical toric variety. So, well, this I also don't have to say very much here, but in fact, the situation is slightly more general than polytopes. You want to consider fans and the toric varieties associated to fans, not only polytopes. And again, the basic idea behind the field of quantum toric geometry is to reply all the tori appearing in classical toric geometry by quantum tori. Some people call quantum tori non-commutative tori. And just in the same manner in which toric manifolds can be thought of as integrable systems, or quantum toric manifolds can in turn be interpreted as quantum integrable systems. And likewise, for the same essential reason that a version of mirror symmetry for toric varieties can be construed as a parametrized version of T-duality for tori, in the same manner, quantum toric manifolds, we have a version of mirror symmetry in which we have this kind of non-commutative T-duality. In any case, from a slightly different point of view, quantum toric geometry can be thought of as a deformation. With this deformation parameter that will be very important for us throughout this talk, we will have this deformation parameter that is deforming classical toric geometry. So you have classical toric geometry, and you deform toric geometry by this parameter. And many results from classical toric geometry have their counterparts in our quantum generalization. The proof of such results are not entirely obvious. On the other hand, the flavor of theory is familiar. We encounter the usual suspects, quantum fans, quantum lattices, etc. Nevertheless, of course, as expected, there is new phenomena that were not available in classical toric geometry. And one of these, one of the phenomena that has called our attention more vividly is the problem of moduli. Now we have a very nice modular space of toric varieties, quantum toric varieties, and this modular space has very nice properties and can be compactified, etc. We'll get there at some point. Anyway, the basic building block of the theory is, of course, the non-commutative deformation of the classical tori, real and complex, known as the quantum torus, given by a deformation parameter. And we will use a real deformation parameter. And it's interesting to consider a complex deformation parameter, but we'll use, unlike Maxime yesterday, we'll use just a real deformation parameter. And well, this is it was pointed out by Alan Kohn as early as 1985 that this was an important example in non-commutative geometry. So the quantum 2 torus is a non-commutative space. And I mean, of course, you could use the right categories or whatever version of non-commutative geometry you like. But just for shorthand, we'll use non-commutative algebras, maybe sister algebras, modular Morita equivalence. And the whole point is that it has two generators, and they satisfy this relation that make the algebra generated by x and y non-commutative, rather than just xy equals yx. It's a non-commutative algebra. And this algebra can be realized as an operator algebra. This operator algebra actually appears in classical quantum mechanics, like in the 1936, 1926, 1925 papers that gave the Nobel Prize to Born E. Heisenberg. But this is of course written in exponential form as in the 1927 reinterpretation of Hermann Weyl. So we have this that appears as an operator algebra. And when we specialize the parameter h to be 0, we obtain the usual commutative algebra of the traditional one. Anyway, there's a classical, well-known arithmetic condition for dichotomy for the parameter h bar. In this commutation relation, the space is truly non-commutative only when h is irrational. Or when h is rational, its algebra of functions is Morita equivalence to a commutative algebra. So rationality precisely detects the true non-commutativity or quantum nature of the space. Anyway, Kohn pointed out a beautiful geometric interpretation for this non-commutative algebra. It can be thought of as the space of leaves of affiliation. The Kronecker foliation of a slope h bar on the classical torus. So this is the Kronecker foliation. You take the plane R2 and you quotient by the lattice to the torus. And this foliation is obtained by considering all the parallel lines of slope h bar on the plane R2 and take it into quotient. And of course, now you see the same arithmetic dichotomy. If the slope of these lines was rational, then the leaves of this foliation are compact, dense nowhere, and they are torus knots. But if the slope of the lines was irrational, then the leaves are dense everywhere, and they are copies of the real line inside the torus. In any case, this algebra can be thought of as the algebra of functions of the space of leaves of this foliation. So you take this foliation, and now you consider the space of leaves of the foliation, and now you want to consider its algebra functions. Well, it turns out to be this algebra that I described before. We will use this map very much, this exponential map. This will have the immediate consequence in all the theory that all our stacks, all the spaces that will appear for us, will be non-algebraic. And this happens because we have to use this map in very many places. In any case, the holonomy groupoid of this foliation is very important for us, of course. It's what you think it is. You know, you consider the foliation, and you consider points on the torus, and then an arrow between 2 points is a homotonic class of paths from one point to the other in the same leaf. And well, this produces a groupoid, this groupoid has a convolution algebra that is this algebra up to compact operators and all that kind of standard story. Is this algebra that I described? The algebra of this non-commutative algebra is obtained from the convolution groupoid of this foliation. And this, of course, just categorically, the convolution groupoid of this foliation is the same as the translation groupoid of the irrational rotation by h bar on this transversal circle. So you can think of the whole convolution groupoid of the foliation, or alternatively, you can think just of the action of the rotation by h bar on the circle, and these groupoids are equivalent groupoids, and they give the same convolution algebra. So, just as quotient spaces, well, this is clear that I can just take the circle and divide by this rotation. But of course, if the rotation is irrational, the quotient is non-Hausdorff. And this is as topological spaces.
Explain, in the case when the thing is rational, you were saying that this function space is x, y, plus q, y. How am I supposed to think about that as functions on the circle?
Well, it won't literally be functions on the circle. You'll have to do it, but it will be a Morita equivalent. So, you, for example, when this thing is rational 3 times around, well, when you do the calculation, it's a calculation. If you do the Fourier transform, you forget about compact operators, then you will get an algebra that, while not literally functions on the circle, will be Morita equivalent to the algebra of functions on the circle.
Well, how can a function with 2 variables? So your claim is that, let's take the case when you just go once around. So your claim is that functions in 2 variables are x, y, x and y invertible is Morita equivalent to functions on the circle.
Well, I'll say something that will clarify this issue. It's functions on the torus, as I will explain.
Yeah, sure. But you're saying functions on x, y.
Well, let me say this right. Let me say this right in a second. In the rational case, you have a stabilizer at every point, z, and so is z cross s1 cross bz, that is s1 cross s1, that is the torus, not the circle. So it's not functions on the circle, but functions on the classical torus, on T2. I'll say this in a minute. Well, we will use these non-commutative spaces at, we'll interpret these non-commutative spaces as stacks rather than as algebras. There is, we have this, say, the convolution groupoid that I just described, or the groupoid of the rotation of the circle. Then you can get this non-commutative algebra that is for, and you could get the non-commutative space by derived category or whatever. But you could also get the stackification of the groupoid, and the stack, you could also recover the non-commutative space. So temporarily, let's think of stacks as groupoids modulo Morita equivalence. We'll actually have to think of stacks more carefully as things over the side of toric varieties, but I'll say that in a minute. And well, we have 4 avatars for the non-commutative torus. This is what I'm trying to say here. We have 4 avatars for the quantum torus. There is this action of the real line on the torus. Then there is this non-commutative algebra, typically for H irrational. Then there is this stack that is the stackification, the quotient stack of this action on this torus. And this is the stack. This is the object that we will use most often. And then we have the non-commutative space coming either from the algebra or from the stack. So these are these 4 avatars for the quantum torus. So one is a translation Lie groupoid, whose manifold of objects is the torus itself, and the arrows are these pairs of elements. Then there is the non-commutative algebra that I described before. Then there is the non-commutative space that you could think of as a Morita equivalence class of this algebra. And then there is just the quotient, is a non-separated, non-algebraic stack obtained by the stackification of the groupoid. So, and we will use the stack. Okay, so so the stack is this quotient stack or this quotient stack S1 modulo the rotation by H bar. And well, we would like to pass by to the logarithm and to describe very convenient. It will be extremely convenient for us to describe this groupoid by this quotient, where we are dividing R by 1, obtaining the circle, and then by H bar, obtaining the rotation. And here is translation by 1 and by H bar of R, the real line. So this will be our model. This stack here, and of course we're using this exponential map. This stack here will be our model for the quantum torus. And well, this motivates the introduction of quantum lattices. Now, as they appear in the theory of quasi-crystal, they are also called quasi-lattices. But I will call them quantum lattices, and then sometimes I call them Q lattices to avoid the confusion. In any case, this is this lattice is quasi-quantum lattice is generated. It's just a finitely generated abelian subgroup of the real line considered as an abelian group. And then, well, gamma behaves quite differently when whether H is rational or not. If H is rational, this becomes really a lattice in R. But when H bar is irrational, well, it doesn't. No, this becomes a logarithm of the rotation action. Anyway, this will be our representation of the quantum torus. This logarithmic representation will be the useful representation for us of the quantum torus, R mod gamma. For gamma, a quantum lattice.
But it's only correct as written when H bar is irrational.
Sorry?
It's only a correct statement as written when H bar is irrational.
No, it's okay, but we'll have to fix it. I'll fix it with something called, yeah. This works, but then you want a much better modular space, so you need to calibrate the quantum torus. So this is what we call the quantum torus, and when we take care of this problem, we call it a calibrated quantum torus. But that comes in a minute.
Is this the definition of quantum torus? When H bar is rational, is that the definition or not?
When H bar is rational, yeah, that's the definition of the quantum torus.
So there's no.
Yeah, it's bad. It's not BC. There's no BC. If I don't calibrate it, there is no BC. It's bad definition. So I'll calibrate it. Well, there are variations. We want to take the complex numbers rather than just the real numbers. So this will be, let's take irrational to relax everyone. Let's take H irrational and then this will be the version of our C star. What we started C star cross C star cross C star cross C star. Our C star will be this. This will be our version of C star, and this will be our version of and here, of course, there could be all sorts of problems with rationalities and irrationalities. We have to fix it. But this will be our version of a quantum torus in dimension, complex dimension D. This will be a quantum dimension D complex torus. And of course, this comes from affiliation, and this is the transversal to affiliation, and this is the logarithmic representation to this transversal to this foliation, but just in higher dimensions. Okay, so now we want to do quantum P1, and just wait a couple of minutes before calibration will fix everything. Calibrations will fix everything. But anyway, we have to put a germ, as you are pointing out correctly. We have to put a germ additionally to this information to fix the situation, to fix the non-commutative degree of freedom. Anyway, quantum P1, CP1 is C star, union 0, union C infinity, union infinity, and we want quantum P1 to be this quantum torus, union 0, union infinity, this quantum torus, but notice that now I switch, and this has to do exactly what that problem. I switch these two for this one, just by notation, but of course this has a reason. This is exactly this. This is exactly this. But now I put a 1 so that this is a CP1. So, but what do we mean by this? Well, let me try. Let me just say temporarily, and then I'll do it much better. Temporarily, let me just say that CP1 has two shards. This shard, and H is irrational for the moment. H is irrational for the moment. So I take X to the 2 pi I gamma and divide C star by that. And I divide C star. Of course, these actions are, the quotient is non-Hausdorff as a topological space, but it makes sense as a stack. So I take this, and this map does make sense at this level. I'll end up with a quantum projective line that is a compactification of this quantum torus. And you want, this is not literally correct, you know, but you want to imaginatively think that pi 1 of this thing is gamma. But of course, it seems to have too much rank. So now that's where I clarify all this confusion with the 2, the 1, the rational, the stabilizer, and all this story. So the naive dimension seems to be a dimension of the torus minus dimension of 1, the real line 1. And this is why we put this 1 down here. Nevertheless, the homotopy type is given by the homotopy quotient, and this thing is contractible. So the homotopic dimension seems to be 2. And this is why we put these 2 here. And this is reflecting the periodic cyclic homology for this non-commutative space. That it will look like the torus. So it will have also this will also have an naive complex dimension of 1 and a homotopic dimension of 2. This CP1. Moreover, perhaps it will clarify the situation a little bit. We will describe a complex manifold like this, and that essentially for CP1 is S1 cross S3, but S1 cross S3 has a complex structure. Nevertheless, of course, S1 cross S3 N cannot possibly have a symplectic structure compatible to this complex structure. So N, that is S1 cross S3, is not a Kähler manifold, but it is a complex manifold. But this complex manifolds comes together with a foliation, a holomorphic foliation. By the theorem of Heffliger, this foliation is holomorphic. So this CP1, in our first example, turns out to be this. So you have this holomorphic foliation in this torus. You have this two-dimensional complex torus, and now you have this complex Kronecker foliation. And magically, there is a compact complex manifold, not scalar anymore. The torus was scalar, not scalar anymore, that compactifies the torus and compactifies the foliation. And so the foliation gets extended to S1 cross S3. N is S1 cross S3. So the foliation, the Kronecker foliation, gets extended to all S1 cross S3. And this holomorphic foliation, well, it's a Hopf surface, of course. This holomorphic foliation has an action. The leaves are the generic leaves look like C, like a copy of A1, a copy of the complex plane. And so now it has an action of the complex plane, this complex manifold, this Hopf surface, and the quotient of the Hopf surface by this action of the complex plane is this stack. Is what we and now, because the foliation is holomorphic, the action is holomorphic, the manifold is complex. This thing ends up well, it's a little bit better. This ends up being a Kähler stack, highly very non-separated, nevertheless a Kähler stack. So and this kind of explains the phenomenon. Okay. Let me say it. Let me say two more things that further explain what's going on. Hopf surfaces have generalizations in Calabi-Ekman manifolds, and they are non-Kähler. Topologically, they are the form S2n-1 cross S2m-1. And they are the formations of an elliptic holomorphic vibration over Pn-1 cross Pm-1. We are, of course, in n equals 1, n equals 2. But of course, this is a toric variety. We have this elliptic holomorphic vibration above this toric variety. One may wonder, is it the case that every classical what happens when I deform this into the non-commutative realm? What happens when I deform this into the non-commutative realm? And say in the case n equals 1, m equals 2, this is P1. And I'm deforming P1 into these non-commutative P1s. So what happens when I deform this into the non-commutative realm? This stays exactly the same. This manifold stays constant. It's just a complex manifold that remains constant. But the elliptic vibration unwinds into a vibration by leaves that are the complex plane, no longer elliptic curves. It unwinds in its universal cover of the elliptic curve. And now the leaves are dense all over the place often. So this unwinds and goes all around this place. But now the leaves are dense in regions, and it's a much more interesting holomorphic vibration, holomorphic foliation. And at vertices of the polytope, in this case, the extremes of the interval in this example that we're thinking about, it winds again into an elliptic curve. But outside, it just goes around into dense regions of these Calabi-Ekman complex manifolds. And it's very natural to ask whether this has a generalization. And it does, and it was discovered by Lvm Meersseman and Verjovsky, two of the co-authors of this paper that I'm talking about. And they discovered that every toric variety has something that this Calabi-Ekman analog, this analog of product of spheres, that is complicated. It could be product of the spheres and connected sums of spheres and all sorts of things, usually constructible with spheres. Above every toric variety, there is this, but it's no longer called a Calabi-Ekman manifold. It's called an Lvm manifold for Lopez de Medrano, Verjovsky, and Meersseman. So there is this Lvm manifold above every toric variety, And there is this canonical foliation on this Lvm manifold that is God-given. The foliation is totally God-given. And this holomorphic foliation is a holomorphic foliation by abelian varieties, by higher versions of this. But still all the leaves are compact in 44. All the leaves are here, all the leaves are compact. When we deform P1 into the non-commutative realm, the leaves are no longer compact. And well, this is what's going on here. When I deform any toric variety into a non-commutative toric variety, all of us, the Lvm manifold remains constant, but the foliation becomes more complicated because now the leaves are not compact. So, but one can say this, one can think of this a little bit to fix this problem with the stabilizers and all this story. Situation is that even the 0,1 is convenient to think of as P1 together with a germ. Even just P1 at h equals 0 or any rational number to fix the modular space. You're totally right. It would be a disaster to have at every irrational point this loss of the dimensionality loss. And to fix this problem, we add a germ at every rational point of the modular space. So every rational point has these classical P1s, all the weighted projective spaces, all the teardrops and the footballs we get there at the modular space of the P1s. As I deform the P1, and this is a long-range deformation, it's just all deformation, it's not a infinitesimal deformation. So I deform P1, H bar is a large parameter, I travel in the space of P1s. Every time I hit H bar rational, it's a weighted projective line, but then I add a germ to fix the modular space. I don't know if this kind of answers your question. So I add a germ to fix the modular space. And in this case, a germ with an abelian band Z. And this explains this difference in dimension by 1. In any case, we refer to this process as calibrating P1 to obtain CP0. It's a beautiful theorem that we have in our latest note. It's not very hard, but it's beautiful that the category of classical toric varieties embeds, it has a fully faithful functor to the category calibrated. So the classical case, you could always have thought it calibrated, and you would have gained or lost nothing. It's unnatural in the classical case to think it as calibrated, but it's useful to think it always as calibrated to be compatible with the non-commutative deformations. In any case, it's a germ over CP1 with abelian band Z. Calibration is by no means unique, but there is a preferred one actually. There is a section to the space of calibrations, and I try to say this here cumbersomely, saying that you can recover one from the other naturally. From the point of view of homotopy theory, this is more or less taking the twofold homotopy cover of P1, but the complex one. So you ask yourself, what is the smallest complex manifold? That is the 2p homotopy cover of P1, and you recover this abelian surface that is a Lvm manifold. That is the Lvm manifold associated to P1. In this case, it's all these names. So that's the story with the gerbs and the calibrations. In any case, but if you got confused with all this story, ignore it and just think of classical toric geometry. And what I'm saying is that you can do like you do in classical theorem geometry. It's all I'm trying to say. So,
in general toric variety, I should add one circle per dimension.
Yeah, I'll say it in a minute. I'll have the theorem, the exact number. Yeah, you're right. Well, to recover CP1, what do we do? We used to have this fund, 0 or plus or minus, together with the integral lattice. And to reconstruct CP1 H bar, we need, and now again, think if you, all that story was confusing just assume h bar is irrational, and you still have the same fun, but now the lattice is not Z, is the quantum lattice gamma. So, but now I have to say this a little bit better. I have to say, I will iterate saying it better and better and better until I say it right. So I'll consider the toric side. So we have this, the toric side of a fine toric variety is what you expect it is. So we have a fine toric variety, and then you do, well, you have a fine toric varieties, and we say that a Zariski open set is toric, if it is toric. We take as the base category for our stacks the category of affine toric varieties and toric morphisms. And we take for covering of an affine toric varieties a decomposition into toric Zariski open subsets. And with these coverings, this is the toric side. We call it the toric side. And we also need the equivariant analytic side. So they are complex analytic spaces endowed with a holomorphic action of a complex abelian Lie group. C, you must think of C star, C star, C star, or copies of C, CM cross C star to the M. That's what I mean by G. CM cross C star to the M. Doesn't need to be compact, of course. And they are equivalent holomorphic mappings. And then there is a natural fully faithful functor from here to here, of course. And by a cover of an object here, we mean an object here, endowed with a proper, free and proper holomorphic action of a discrete abelian group, whose quotient is T together with a map, which is a non-ramified analytic equivariant cover of T. It's exactly what is exactly the situation that we are encountering when we open the lips of the foliation. Okay, so this is the equivariant analytic side. And now quantum Taurus stacks are of the form X mod H, with X in the equivariant analytic side, and H a discrete abelian group or a complex abelian Lie group. And then, to be more precise, we consider the category whose objects are covers T of space T, T lives in the toric side, and an equivalent holomorphic map. It's very natural. Okay, here is assumed to be equivalent with respect to both the H action and the G action. And morphisms are this kind of commutative diagrams. And now, well, quantum toric stacks will be this kind of thing. But it's perhaps better to do an example, because that could be a little bit confusing. And D equals 1, this should be the equals 1. And define gamma as a subgroup generated by 1, and H bar is equal to square root of 2. Just take H bar equals to square root of 2 irrational. So since square root of 2 is irrational, it returns in R, it acts freely in R by translation, and it's not proper, and the topological quotient is not Hausdorff. So the action is not separate. This is not a manifold. But it behaves well in this category of things that we just defined, because T is CD mod gamma, as I explained in the logarithmic representation, the universal covering of the transversal to the Kronecker foliation. And I'm losing, this thing is not working anymore. I'll try this here, I guess. Yeah, this works. And this is a category favored over the tropical side, and the objects are gamma covers of T over the space A with an equivalent holomorphic map like this. The important thing is that if I have this gamma generated by 1 and the square root of 2, this linear map in the logarithmic representation has Gauss descent. And now I can do this kind of monoids where the exponents are irrational numbers. So now I have these monoidal algebras where the exponents are irrational numbers, and this makes sense. This makes perfect sense. So the whole point is that W to the square root of 2 makes sense for these objects. and I need the exponential map to write it like that. Of course, I need the map E. In any case, classical P1 is obtained by gluing two copies of the affine toric variety C along the Zariski open set via the map Z1/Z. And in this language, it can be seen as a category fiber over the toric sides. So in the obvious way, there I have the only diagram you need to see it as a category fiber over. So, but in few words, what I'm saying is that the classical gluing instructions of a fan give you the way to obtain a variety, indeed, traditionally, if the thing was rational. But they give you the way, they give you exactly the same as the sent data on this category of toric stacks. So you could either glue your variety or consider this as this fan as the sent data. But it's more general, the situation with stacks, because now you don't need the fan to be rational. The fan can be irrational, and they still give you good descent data to produce one of these quantum toric stacks.
Can you say what is it? Before you said torque site, well, torque orbit. What is torque orbit?
Sorry, I said it here. There it is. 2 point. Huh?
You said the objects are affine torque varieties. What is the torque orbit? I just want to know what is a torque orbit.
Well, it's just an equivariant map, an equivariant analytic map. Well, the torus is always acting, isn't it?
Two torque varieties have different varieties. Torque orbit means that first it's not tori and then it has
Well, yes, I have to be careful, but I can do all the details for you later. But it works. It's a long verification, and yes, it needs clarification of some of these details. But let me just move because I'm starting to have very little time. I can talk to you later. So, so you have this descent data, and the whole point here is that, well, classical P1. And now I have to go a little bit fast. I'm very sorry. So, so this is a quantum fan. So a quantum fan looks like a fan, but unlike the classical fans that had these lattices here, the classical lattices, a quantum fan lives on a quantum lattice. It lives, it just, and of course, in the past, you could take the shortest primitive vector here. Now you need to mark the point. Now you need to mark the point. And because we want to add these Yerb degrees of freedom so that everything works fine, so that there is no problem, then I really am going to really work with calibrated quantum toric stacks. And a calibration looks like this. A calibration is actually H bar. H bar is our degree, our deformation parameter is the calibration. So H, no longer H bar, now I call it H, is a map from Z to the N to R to the D. And the canonical generators give me these vectors. Sometimes they have to cover all the one rays of the fan, but they could also be a little bit additional vectors there, additional degrees of freedom, and that's okay. So this, if you want to think of this in terms of these integral systems, it's kind of funny because now you have various Planck lengths of the quantum system, but geometrically H is this map from this lattice in higher dimensions to these are typically N is bigger than D. Typically N is bigger than D. So we need to do the calibrated thing. And here, calibrated quantum torics, if you had a classical toric variety, it's a Yerb with band Z to the A, as you said. It's a Yerb with band Z to the A. And then, well, so here is n minus rank z of gamma, where n is the dimension of this higher dimensional lattice. So now I'm going fast. I'm sorry, I guess. So example, now we would like to do not, well, this is more or less the same example. Now instead of the square root of 2, I'm doing a. And but what is interesting is that now I can vary this h. This is my deformation parameter. H is my deformation parameters. And as I move h, I will get a chart for my modular space. And so here I start moving a, that is moving h is given in terms of a. And as I move a, I get rational and irrational a's. And for the rational case, well, I have this germ as well. And I get, well, the weighted projective lines. And for the irrational ones, I get the quantum projective lines. And the weighted projective lines come together with a germ, but the germ is totally topological, it's totally canonical, non-commutative degree of freedom. So,
even though the tori are the same for rational numbers, these projective P1s are different.
There are different compactifications. Okay. There are different compactifications.
Okay.
Just like the weighted projective are different compactifications of C star. There are different compactifications of C star, but they are orbifolds typically in the rational case. In any case, we get if we get now think of this fan where E1 is this now this lives in R2. You get E1 is E1, E2 is E2, but B3 moves freely and has 2 degrees of freedom. The third vector moves freely and has 2 degrees of freedom. When A and B are -1, this is a classical fan for P2. But now as we move A and B, we are all these quantum deformations of P2. And we get these 3 maximal cones. These are the 3, and we get these three quantum toric charts. This, if you take 0 and 0, you take the torus inside C2. These are 3 quantum tori that are the same quantum tori. They look different presentations, but they turn out to be the same quantum torus. And so you can glue these 3 same quantum torus into one quantum torus. If this was, you took the torus inside here, and but now you can do this kind of calculations, these monoidal calculations, where A and B are irrational numbers. Now you can do them; they are legal, and now you get all these deformations, these 2-parameter deformation space of the classical thing. In any case, but the important point is that if I take the torus here inside, these are 3 different presentations of the same quantum torus. And of course, well, because you have the GL2Z acting, of course. Now, all of these numbers could be irrational. The transformation between them have to be integral. In any case, this is the category of simplicial calibrated quantum toric varieties, and is equivalent to the category of quantum toric fans. So this is a theorem that we prove. This is it has been constructed to be the case. Now we have geometric invariant theory, quantum geometric invariant theories. The calibrated case is an important case. The non-calibrated case, it's too singular, too irregular. So the calibrated case is the important case. And so we have this fan and this H, that is our deformation parameter, our H bar. This H homomorphism from a higher dimensional lattice to RD, from Z to the N to RD. and gamma is the image of H. It's a quantum lattice that is the image of H. And so we can do the Gale transform. So if we have H, we can do the Gale transform and get the A's, namely the K. So we get the K, we have the H, we get the K. So we do the Gale transform. And we can define the typical situation. This thing kind of, the battery kind of dies. We can define this typical domain that is as we take this is this is the same thing as always. This is an affine toric variety. And now we can put an action using the Gale transform on this. And so this action that came from the Gale transform, A is the Gale transform action of H, gives me a global quotient stack. And these stacks are the same. So this is a geometric invariant theory of producing the quantum toric, calibrated quantum toric variety. What, sorry?
Make it as mod
A is a Gale transform of H. A is a Gale transform of H.
How does the quantum parameter?
H is a quantum parameter. H is a quantum parameter. Here is the quantum parameter. H is a morphism from Z to the N to R to the D. H is a quantum deformation parameter. A is a Gale transform of H. And A produces an action. A produces an action on S. It's a good action on S. The Gale transform of H produces this action on S. And then you have that S molded out by the Gale action, the Gale transform action, is the same as the calibrated given by these charts that I described. So this is a way to define the stack without the charts, just once at a time. That is analogous to the geometric invariant theory, the classical geometric invariant theory.
So my question is, this S, does it depend much on the quantum parameter?
No, it's the combinatorics of the fan. Just the combinatorics of the fan. This S is in the classical toric geometry the same S, I believe. Just the combinatorics of the fan gives you S.
Like Cn plus 1 for En or?
Cn is Cn minus things. Cn minus some.
Yes, yes.
The unstable, yeah. I'm taking away the unstable level. But the beautiful thing is that the Gale transform gives you exactly the action that you need to produce this this stack. So this is geometric invariant theory. And essentially geometric invariant theory is given by the Gale transform. And there's the uncalibrated version as well, that is uglier, but if you want the uncalibrated object, you can do it and recover the classical toric variety without the gerb. I don't know why you would want it, but some people want it. And it is still the Gale transform, and it's the same. Now you think of this action as a foliation, not as an action. Now you think of this Gale transform action as a foliation on S. And the space of leaves of the foliation is exactly the classical toric variety in the rational case, without the gerb. And in the irrational case, it makes no difference, of course. So, and now this is what I just said before about this magical manifold that is above every toric variety, but now it's above every quantum toric variety. And if you don't change the combinatorics there, so you carry this manifold, and what you are burying is the foliation. Is the foliation inside the manifold, not the manifold N, as you deform the toric variety into non-commutative toric varieties. So what you are deforming is the foliation. The uncalibrated thing is the space of leaves of the foliation, and the calibrated thing is taking the CM action that has a little bit more information than just than just the foliation. In the earlier papers, there is this foliation that is canonical, but if you think about it, it really has a preferred action, a preferred parametrization, the foliation. And if you take into account the parametrization, you get the calibrated case. So, well, the thing is that from the Lvm manifold, you can recover as well the in the other case, you were taking this complicated complex domain and putting this action, simple action given by the Gale transform. Here you are taking kind of a transversal thing. You are getting a very nice complex manifold N, and restricting this action, and you get this story with this very nice complex manifold N. That is a generalization of the Calabi-Ekman manifolds, the Lvm manifolds. And so this is the story. And a theorem using some results of Ishida, one can prove that the toric stack is scalar if and only if the fan is polytope, which is to be expected, but kind of nice to know that is true. So the scalar stack is the quantum toric variety is scalar if and only if the fan is polytope. And now I will go, unfortunately, I think I have to go very fast and I won't get to the mirror at all. No, I won't get to the mirror at all. But anyway, now I just said you can do modular spaces. You can do modular spaces. Yeah, you can do modular spaces. And if you do it carefully, there is many parameters to do in the modular space, but if you do it carefully, you get these beautiful orbifolds, complex orbifolds. The modular space are complex orbifolds. And the rational points of the modular space are the classical toric varieties. And every other point of the modular space are the quantum toric varieties. So the rational, for example, in the P2, the rational points are the weighted projective P2s, and the irrational points are the quantum. But of course, you have to carry the gerb to make a nice modular space. Otherwise, it would be too singular. It would not be an orbit. So you need to do the calibrated version. Categorically, it doesn't matter. And we have something like the Teichmüller space, of course, for this modular space. And let me just move to let me introduce Antoine's talk. Your talk is on Thursday, the last talk. And he will continue with this talk. No, not that. He will continue with this talk. So we have this Teichmüller space, and ignore the D. N is the number of gerb that you put, the rank of the gerb that you put, and D is the combinatorics of the fan. So in the classical modular space, you had MGN. G was a topological thing, but it was a combinatorial thing of the surface. G was a combinatorial thing of the surface, and then a desingularizing number of mark points to make the modular space nicer. You put these endpoints, and then the modular space gets nicer. If you don't put the endpoints, it's not as nice. So we have exactly the same situation here. We have, ignore the D, ignore the lowercase d. The D, capital D is the combinatorics of the fan. That's the genus of the toric variety. I claim that the genus of the toric variety is the combinatorics of the fan. And that in the classical case, the genus determines the topology of the Riemann surface. And here, the combinatorics of the fan, well, you see. So the combinatorics of the fan is the genus, is the analogous to the genus. The D doesn't matter. The N, you had N mark points in the classical modular space. Now you have our N rank gerb to make nice the modular space. If you don't put the gerb, you get this very bad thing, as he noticed very early. But if you put the gerb, then you get a much nicer, an orbifold. You get these orbifolds. And you get the modular space. And let me just say that we have results on the modular space. This is a typical result. For example, for Pn and all its deformations, we get a nice modular space. and we get a nice universal family over all possible PDs. So we get all the possible PDs, and we get a nice universal family of all the possible PDs. In this case, we understand the whole modular space very, very, very well. But of course, it gets harder and harder, and you want to do fancier modular spaces of other toric varieties and all their possible deformations. Then you would have to, in all these, we only consider the simplicial case. Luckily, Antoine has considered the non-simplicial case, and he has been able, I believe, to compactify. Well, I was explaining how to compactify the modular space. It's a beautiful story, how you compactify with this geometric invariant theory, the whole modular space for the PD, or this is for the P2, but I'm out of time. In any case, Antoine Boivin, the talk, I think this is the term of the next talk, isn't it? You will compactify the modular stack of all in general, not only for the PDs. We did the PD, and then he did the general case. And I ran out of time, and apologize.
So what is the dimension of this moduli space for PD?
Probably Antoine knows this better than me. This is easy, but the letters. It is. There it is. There it is. There it is.
What kind of Meersseman do you have?
Well, now we have all these. Now we don't have just tori. I'll talk to you later. Yeah. But Gabe Kerr also knows lots of these things.
So in this moduli space, so the kind of like the pan, what you call genus is kind of fixed.
The combinatorics.
The combinatorics is fixed.
It's fixed.
So it cannot like degenerate to some other type.
Well, when you compactify, it does.
It does.
When you compactify, it does. Look, when you compactify, it does. Yeah. Because you have to add this, like in MGN, the genus, like in MGN, you have to add all these things for the compactify the modular space. Here too, it's very beautiful.
Yeah. Thanks again.
Thank you very much.